Hello students, welcome to this massive open online course on advanced analytical techniques, and today we are going to study the last unit of this course, that is the gas chromatography. So gas chromatography is actually an advanced version of the elution chromatography which we have already covered in our previous slides. So let us begin our journey of gas chromatography. Gas chromatography, like the elution chromatography, is an analytical separation technique, and this technique is very much specific for the separation of volatile components of a mixture. This technique, gas chromatography, involves both, as usual, the mobile phase and the stationary phase. The only difference here is the mobile phase. In gas chromatography, mobile phase is exclusively gas, and this gas is generally referred as inert carrier gas or simply carrier gas. So chromatography gives you an idea of separation of volatile components, and again here the separation is based on the difference in the affinities of different volatile components with regard to their interaction with the stationary phase. And this stationary phase may be a solid or it may be a liquid. And in the coming slides, we are going to have a broad classification of this gas chromatography on the basis of the stationary phase. So let us explore this race of volatile components along the column as they travel with the inert mobile phase. So gas chromatography actually has three main components. One is the pressurized tank which contains the carrier gas. Second is the detector system, which is actually called as the heart of the chromatography, of the gas chromatography, and the last one is the detector, which may simply be regarded as the visualized state, or you can say in simple words, the eyes of gas chromatography, or in simple words we are going to call it GC, that is gas chromatography. So with this, gas chromatography is of course an analytical separation technique where the different components of the vaporized sample actually gets partitioned between the mobile phase and the stationary phase. Here this is similar to the previous, that is the simple elution chromatography. The basic differences or the key aspects of this gas chromatography are: number one, that is here high temperatures are involved, that is we have to vaporize our sample. If it is present in the liquid state, then initially we have to get it vaporized so that it can travel along with the inert mobile phase. Second is, of course, here the inert gas should only act as a simple transmitter of your analyte through the column. So basically here the separation, or you can say the elution, is based on the pressure of the inert gas which it carries, and it mixes with the, you can say, your sample, your vaporized sample, and then your vaporized sample passes through the column, and in the column actually it gets partitioned. While in the elution chromatography it was the simple gravitational pull where your elution is going to happen, or which happened actually. So here the main principle is again the same. The components of sample get separated on the basis of the difference in their partition coefficient. Okay, so again this gas chromatography is both, it gives you an identification of different components present in the vaporized sample, it gives you a qualitative idea, and third, and the important one, is that it gives you the quantitative idea of the different vaporized components present in the sample, which is getting partitioned between the mobile phase and the stationary phase through the column. Okay, broadly speaking, the gas chromatography can be classified on the basis of the nature of a stationary phase. For example, if the stationary phase is simply a liquid immobilized on the solid surface, then we call it the gas liquid chromatography, that is GLC. In simple words, it can also be said as the GC. So here the stationary phase is the liquid, or which is impregnated or which is immobilized on the solid surface, and the principle of separation of different analytes is the difference in the partition coefficient, and this is very useful for the separation of an array of organic compound. This is, you can say, generally used technique. Generally we use GC for almost all organic compound, almost all organic compound, you can say like this. While in the other one, that is called as the gas solid chromatography, here the solid or the stationary phase is a solid, and on the solid surface the component gets adsorbed. So here the principle of separation is the adsorption. This technique, that is the GSC, is limited for the separation of small volatile components, that is having the small molecular weight, for example certain gases like carbon dioxide, like ammonia, like sulfur dioxides, and various nitrous X's. The problem with this is that since here the components of the sample gets adsorbed, so this type of gas chromatography, this type of chromatography is actually gives you some sort of tailing. Here tailing becomes dominant in certain cases, and because of this GSC is avoided for the identification as well as the quantitative and qualitative analysis of most of the organic compounds. So most of the time we will be using this GLC, and this GLC is simply referred as GC, that is the gas chromatography. GLC has many very good features, and the best one is that it has very good reproducibility. Reproducibility means that if you are going to carry out your separations for 5 cycles or for 10 cycles or for 20 cycles, the results will remain the same. Similarly, it has very good selectivity because the different components of your mixture actually gets partitioned, and this partitioning is because of the affinities of different volatile components with the stationary phase, with the inert stationary phase. That is what happens in GLC, that you have a stationary phase, solid stationary phase, and some liquid is actually immobilized on that surface. So what happens is that now your partitioning actually occurs between the carrier gas, which is called the mobile phase, and the liquid, which is immobilized on your solid support. So this type of separation actually occurs, and it gives you selective type of separation, and we are going to see this, that how this GC is better than our previous elution chromatography in terms of resolution, in terms of selectivity, in terms of lesser time for the running of the experiment. So we are going to see all these advantages of GC or simply GLC on elution chromatography as well as on the GSC, that is gas solid chromatography. Let us start with the principle, which is very important. Again, the fundamental principle of GC remains the same as that of elution chromatography. Here the main difference is, of course, that here the sample must be in the vaporized state. That is, this chromatography is very good for the separation of volatile sample. Now, in a broad sense, a volatile compound may be defined as a compound which is actually remains in the gaseous state at room temperature. For example, low molecular weight hydrocarbons, they are the best example of the volatile compounds. So this type of GC is very beneficial for the identification and for the quantification of the components of a vaporized sample. So here the sample gets partitioned between carrier gas and the liquid stationary phase. This liquid stationary phase is that which is actually immobilized on the or the inert solid support. Most of the time we use diatomaceous earth or silica or glass beads as the solid support, and we actually immobilize it with certain stable liquid. So here the partition occurs between the liquid stationary phase and the inert. So again the concept remains the same, that is the strong interaction. If the solute molecules, that is the vapor in the solute molecules present in the vaporized sample, if it is going to have a good interaction or a strong interaction, then they are going to stay for longer time. And if they are going to stay for longer time, then they have high retention time, that is TR. Now it is very important to note that here in GC sometimes we also use VR. Instead of TR we use VR, that is the volume of the retained species, and this VR is actually called as, it may be defined as VR is equal to F into F multiplied by TR, that is the flow rate. Similarly, for unretained species we call it VM is equal to F into Tm. So in certain cases while discussing the GC we use these terminologies, that is VR and VM instead of the TR and TM, and this is the relationship between VR and TR. The TR is actually the retention time and VR is the retained volume. Similarly, VM is the unretained volume and TM is the time taken by the mobile phase alone. If you remember it from the previous slide, for example, let me draw it again. What happens is that on the y-axis you have plotted the detector response, and on the x-axis it was the time. So if you have a two component system, for example, then your chromatogram would be like this. So this distance, if you drop a perpendicular, so this distance was Tm, and this distance, half of this was called as TR1 and half of this is called TR2 for a two component system. For example, if you have a single component, then what you can do, you can erase it, you can erase this line, and simply you can do like this, simply you can have like this. Okay, so that was actually the distinction between TR and TM. This is called TM, that is the time taken by the mobile phase alone, that is the time taken when the mobile phase have no interaction or zero interaction with the stationary phase. So that was TM, and the replica of TM is here VM. Similarly, the replica of TR in GC is VR. So again, coming back to this principle, so if the volatile component is having a weak interaction, then it is going to elute fast. Elute fast means that is it is going to come out from the column very quickly, and if it is going to come out very quickly, then it will be having shorter retention time. Okay, so the main aspect on which this GC is dependent is again the partition coefficient, and the partition coefficient can be simply defined as Cs upon Cm, that is the molar concentration of your analyte in the stationary phase divided by the molar concentration in the mobile phase of your solute. So you can also define it like this: number of moles of solute in the stationary phase divided by volume of solute in the stationary phase divided by N of mobile phase upon volume of mobile phase. So you can define in terms of number of moles of solute, that is Ns, divided by volume of solute in the stationary phase upon number of moles of solute in the mobile phase upon volume of mobile phase. So you can actually define this partition coefficient in a number of ways. You can also define in terms of activity. Okay, so you can define it in a number of ways, but again there is a problem, and the problem is that you cannot measure it directly. We have already discussed it at length in our previous unit where we have exclusively discussed the elution chromatography. So, what you have to keep in mind, you have to convert and you have to derive certain equations where you can measure this distribution constant. This is also called as distribution constant. Sometimes it can also be replaced by Kc. So, because it is the equilibrium between the stationary phase and the mobile phase by the solute molecules. Here your solute molecules are of course the volatile components. Okay. So, you can define it in a number of ways, and now in the coming slides we are going to see equations which involves Kc and some measurable quantities, and the measurable quantities are Tr, Tm, Vr and Vm. So, we are going to discuss these measurable quantities and we are going to define Kc or simply K in terms of these measurable quantities. So, let us embark our journey that what is the step by step procedure of doing gas chromatography or simply GC. So, initially we have a sample injection port, and the main work of this sample injection port is to mix your vaporized sample with the carrier gas which is coming from the pressurized tanks. So, sample injection port where your vaporized sample gets mixed with the carrier gas which is coming with a certain flow rate, which is coming with a certain pressure, and it got mixed, and then your solute or your vaporized sample gets transported through the column to get a good separation. Similarly, transportation, that is the main role of your inert gas is to move your analytes into the column. Okay. Then when your sample enters into the column, then the partitioning occurs. Okay. Then each compound gets distributed between the gas and the stationary liquid. Mind that stationary liquid is actually immobilized on some inert solid. Okay. So, here the main work starts, that is here the distribution or you can say equilibration of your components occurs between the gas or the carrier gas and the stationary liquid. Then of course separation takes place, and this separation occurs on the basis of the difference in the volatility or the affinity with the stationary phase, and this difference in terms of volatility and affinity give rise to difference in their interaction with the stationary phase, and this difference leads to the difference in the retention times, and this difference is actually gives you a good separation. Greater the difference, greater will be the separation, better will be the efficiency of your column, or you can say better will be your GC technique. So, then comes the detection, which I have already referred, that is called the eyes of GC. Here each component actually exits the column separately, and each column appears as a peak. So, detector gives you each component in the form of peak. For example, if your sample contains 2 components, then you get 2 peaks. Like this, you get 2 peaks. If your sample contains 3 component system, you will get 3 peaks. Now, this gives you an identification, and this also gives you a quantitative idea, because the area under each peak gives you the amount of that particular component present in your volatile sample. I am emphasizing every time volatile, because this technique is very good for the detection of volatile samples. Now, if for example, if your sample is a liquid, simply let us suppose a case that your sample is actually liquid, then initially if your sample is liquid, then first of all you have to vaporize your sample so that your vapors, your sample vapors get mixed with the carrier gas, and then they can be transported to the column, and in column actually the separation occurs. Okay. So, a chromatogram may be defined as a picture of the various components in the form of peaks and where each peak is actually telling you the presence of each or a particular component, and the area under that peak gives you about the amount of that component present in your sample. Okay, so chromogram is actually a pictorial representation of a qualitative and quantitative aspect of various components of your sample. Okay, so let us see that how the different components gets arranged in a gas chromatograph. So initially we have cylinders of the carrier gas. This carrier gas must be inert. The most important aspect of carrier gas is that it should be inert in nature. Okay, so most of the time we use helium, we use argon, but sometimes, because these gases are very expensive, so sometimes we use nitrogen also. But the problem with nitrogen is that nitrogen gives you poor resolution. It gives you, it gives you some type of blurred peaks. So nitrogen is avoided. And in some cases actually we use hydrogen also. Although hydrogen forms explosive mixtures with certain compounds. So the foremost aspect of a carrier gas which we are going to see is that it should only act as a transporting material, nothing more than that. Okay, so initially we have a carrier gas, and then this carrier gas which is packed in column, which is packed in cylinders, then it goes to flow controller. Now flow controller is very important because these are the flow controller actually controls the flow of mobile gas, you can say mobile gas or the inert gas, because this flow rate, if you do not control it, then your retention peaks or your peaks are not uniform. So in order to have a constant flow of your mobile phase, you need flow meters. Sometimes they are also called as rotameters. And in flow meters, we use certain substances to actually purify, so that our carrier gas can be purified before mixing with the sample. So sometimes we use gauges, sometimes we use sieves to filter out the impurities, and this can be done at flow controller. So then from the flow controller, your inert gas or your carrier gas goes to the injector or the injection system, where it mixes with your volatile sample. Okay, so here actually your mixing occurs, and since the volatile compound is in the gaseous phase and your carrier gas is also a gas, so you have a very good diffusion and transportation of your sample, of your volatile sample occurs, and it transfers it to the column, which is actually inside an oven in a temperature controlled condition. And this temperature maintenance is also very important, which we are going to see in the coming slides. And from the column it goes to outlet, and then finally comes the roll of recorder, which gives you chromogram, in terms of the number of components and in terms of the amount of various component present in your volatile sample. So from column it goes to outlet, and then you get the recording in the form of chromatogram. So here you get chromatogram. Okay, so flow controller, we are going to discuss it. The main aspect of flow controller is that it gives you constant, or you can say consistent gas velocity, and it maintains the your pressure, so that, because if inlet pressure is maintained, then the outlet pressure can be maintained. Okay, so this is important, because if the pressure is not maintained, then a clogging may occur. Okay, so we have to avoid this state. Now what are the components? So there are 6 main components of a typical gas chromatograph instrument. So these are: number 1, the carrier gas system, which has the mobile phase, which is actually your mobile, this mobile phase, which is actually a medium of transportation. Then you have a sample injection system, where your sample may come in the vaporized state. If it is not in the vaporized state, then it must be converted into vapor here before entering into the sample injection port. So then we have the column, which is regarded as the heart of separation because all the separation occurs in this column. Then you have an oven that in which your column is contained, so that you can maintain the given amount of temperature. Then you have a stationary phase. Again, it is a liquid film which is immobilized on some inert solid surface. The solid surface may be silica, it may be alumina, it may be simply diatomaceous earth. Okay. Then we have a data acquisition system where you actually get your chromogram. Okay, so all these components actually are very vital, and you cannot ignore any component because each component has a defined function, and to get a good separation, all these components should work in conformity with each other, just like a human body. Okay, so all these 6 components have to work in conformity, in harmony, so that we can have good separation, good reproducible chromatograms. So we are going to study each of these components in detail in our coming slides. Thank you very much. Thank you.